Hi students, welcome to my lectures on chemical engineering thermodynamics. I request you to follow from the beginning because every lecture is connected. In the last 3 lectures, we have discussed about finding bubble point pressure, dew point pressure and bubble point temperature. In today's lecture, we are going to discuss about dew point temperature. Few steps were common, so I won't explain in detail, so that if you wanted to listen to the dew point temperature, I request you to follow the previous 3 lectures. What is a dew point? Let us say there is a mixture of A plus B in the vapor phase and it is at a certain pressure at 70 kilopascal. The fraction of A in the vapor is 60% and fraction of B in the vapor is 40%. I need to find out the temperature at which first liquid drop is going to form. That is called the dew point. If liquid is forming, at what temperature it is forming, and what is the fraction of A in this liquid and what is the fraction of B is in this liquid. That is our today's agenda. That is why it is called dew point temperature. Okay. Given P, Y1, Ya, Yb. Okay. Y1, Y2 is representing A and B. A is representing with 1, B is representing with respect to 2. Okay, find x1 and x2. That means xa and xb. So acetonitrile is, that means the A component is called acetonitrile, B component is called nitromethane, which is 60% and 40% in the vapor phase. Antoine constants of acetonitrile and nitromethane were provided, and these two are Antoine equations. This is to find out the saturation pressures. This is to find out the saturation temperature. That means boiling points of pure acetonitrile and pure nitromethane. Our agenda is to find out the mixture point. Okay, at what temperature a liquid droplet is going to form. That is called dew temperature. So, if you, as we know, pressure is 70 kilopascals in this container, and if I keep pressure, we can find out what is saturation temperature of A and what is the saturation temperature of B. Saturation temperature of A is 69.84 and B is 89.58. A is here the acetonitrile. That means boiling point of acetonitrile is very low. That way it is called highly volatile. And the other one is nitromethane. It is called less volatile substance. So X1 and Y1 are representing for acetonitrile. X2, Y2 are representing for the nitromethane. Okay, that is why boiling point of acetonitrile is 69 and boiling point of pure nitromethane is 89. So let us find out. There are 3 steps to estimate this dew point temperature. And step 1, okay, you have to first calculate the P1 saturated by assuming the alpha, which is relative volatility. What is relative volatility? I have explained in the previous lecture. So you have to assume alpha first. Based on alpha, you have to find out the P1 saturated. Alpha is nothing but P1 saturated by P2 saturated. That means saturation pressure of component 1 divided by saturation pressure of component 2. It is called the relative volatility by assuming the ideal case, which is called Raoult's law. Okay. Then you already know x1 into P1 sat is equal to y1 into P, x2 into P2 sat is equal to y2 into P, where alpha is equal to P1 sat by P2 sat. I know it's a binary mixture, x1 plus x2 equal to 1. I substitute the above 2 equations in this equation. I get y1 p by p1 sat plus y2 p by p2 sat equal to 1. So let us divide this second term, y2 into p by p2 sat divided by numerator and denominator, you divide it by p1 saturated. Okay, if you do it, then you got here y1 by p1 sat plus y2 by p1 sat, P2 sat by P1 sat, okay, which is equal to 1 by P, okay, and you know P1 sat by P2 sat is nothing but alpha. So this equation will transforms to this 1 by P equal to y1 by P1 sat plus alpha into y2 by P2 sat. Therefore, what is P1 sat? It is nothing but y1 plus alpha into y2 into P, okay. Then you can see this is the equation you are supposed to use to finding out the dew point temperature. So by assuming the alpha, you can calculate the P1 saturated now, which is the first step. You can assume alpha you know y1 which is 60%, y2 is 40%. Then putting the values, you can get the P1 saturated. This is the first step. Second step, once you got the P1 saturated, calculate the temperature, the dew point temperature using the equation, this equation, because everything B1, A1, C1 is here. So you can use this particular equation, okay, and you can calculate the temperature T. Once you calculate the temperature T, calculate the nu alpha, that means new relative volatility you have to calculate. How you got this equation? Equation 1 minus equation 2, if you do a 1 minus 2, you get ln P1 sat by P2 sat is equal to ln alpha nu, because alpha is nothing but P1 saturated by P2 saturated. So using this equation, you can calculate alpha nu. That means you have assumed one alpha, you got some new alpha using this equation. If both are matching, you can stop the calculation. Then whatever the temperature you get it from the step 2, it is called your dew point temperature. Okay, I have done for one case, I can show you. So if you see here, the step 1, assume alpha, find P1 sat. In the second step, calculate the dew point temperature. And 3, calculate alpha nu. If repeat the step 1, 2, 3 till alpha equal to alpha nu. Once the alpha equal to alpha nu, you can stop the calculations or iterations. Okay, I have done it for this particular composition, which is 60% of A and 40% of B. So in the first step, I have assumed alpha equal to 1.2. So according to this alpha, I got the temperature 72.1. Okay, then I have calculated alpha nu. Alpha nu is 2.005. You can see alpha which is assumed, you can see this is assumed, okay. I got 1, then 2, then 1.22, both are not matching because both are not the same numbers. If both are not the same numbers, I take a new guess alpha, which what was the new guess? Whatever I got the alpha nu, that is my second guess, okay. Then using the second guess, again I have calculated alpha nu, it is 1.94. Both are not matching. Again, you take this as a new alpha, again you calculate. You can see in the fourth step, alpha which is assumed 1.9, which is the alpha nu is also 1.947. That means alpha, now both are matching, that means you can stop the iteration. So during this step, last step, whatever the temperature you have received, which is 79.578, is your dew point temperature for this particular composition, which is 60% of acetonitrile. Okay, so once you got the temperature, find out the P1 saturated, P1 to P2 saturated. That means at this temperature, using this equations, calculate T1, using this equations, calculate P1 saturated and P2 saturated. So I got the P1 sat is 96.3 kilopascal and P2 sat is 49.58 kilopascal. Okay, then I know, then I have the next agenda is to calculate x1. X1 is nothing but y1 into P by P1 sat. I know y1, I know P, I know P1 saturated. Then I got 43.5% and x2 it is 1 minus x1, which is 0.565. Okay, that means imagine if I have a vapor of 60% of acetonitrile, if I condense it, it will form a droplet. In the droplet, the composition will reduce. It is 60% of A, but in the liquid, it is 43% of A. Because you are trying to condense it, the purity will reduce, but purity of B will increase. You can see B is 40% in the vapor. How much is B in the liquid percent? I mean 56.5%. Okay, this is what that means. The agenda is to calculate the temperature x1, x2, and you have calculated the temperature, which is x1 here, x2 here. This entire calculation is based on only 60% of acetonitrile. What happens in the vapor? It is 20% acetonitrile, 40% acetonitrile, 80% acetonitrile. For every different composition, you have to redo the calculations, so you get this table. Okay. The fourth one, which I have done on the board, which is for the 60% acetonitrile. Okay, you have to redo the things for the 20%, 40%, 80%. For the y1 equal to 0 means y2 equal to 1. That means this is called the pure boiling point of nitromethane. Here y1 equal to 1, that means pure acetonitrile. Acetonitrile boiling point is 69. If you mix these two, the boiling point range will be in between 69 and 89. You can see here the boiling points, that means the dew points. The dew points are between 69 and 89. So these are the different x1s and different x2s. So you can do the homework, these three, you can do the homework, and once you have formulated this table, plot TXY graph. This TX, first plot T versus x1, second T versus y1. If you plot T versus x1, you get a blue curve. Okay. If you plot T versus y1, you get a red curve. Okay. The graph is, the x-axis is the temperature, y-axis is the composition. It can be x1, it can be y1. So below this blue curve, the temperatures, if you keep the lower temperatures, everything will be the liquid state. If you keep above higher temperatures, that means most of the things are in vapor state. Only between certain temperature, you can find liquid plus vapor. That means between this red curve and blue curve, liquid and vapor both will coexist. So we neither want complete vapor nor we want complete liquid. We have to bring vapor and liquid both at the same time. If then only separation can happen. Otherwise, there is no point. There is no separations going to form. What I have done today, that means I will explain you on the graph. See, Ya, that means acetonitrile in the vapor is 60%. That means acetonitrile in the vapor is 60%. Okay. Then acetonitrile in the liquid is 43%, somewhere here. Okay, 43%. At what temperature these both are there? At the temperature which is 79.5. Okay, around 79 something around, right? If I plot a horizontal line, that means at a constant temperature, if I plot a horizontal line, wherever the curve, this horizontal line touch the blue curve, that's a liquid composition x1. Okay, wherever it touches the red line, it is called vapor composition, which is y1. How much is my x1? X1 here is around 0.43 and y1, which is around 0.6. Okay, 0.6. You can see the line connecting vapor and liquid at this temperature is called tie line. That means at any point of time, if you are trying to say vapor and liquid, okay, Ya is 60%, Xa is 43%. That means at a time you are connecting this vapor and liquid. Okay, the line which connects the vapor and liquid, it's called the tie line at this particular temperature. So there could be number of tie lines. Okay, every horizontal line, if you plot on this graph, is a tie line. Okay, it is connecting vapor and liquid composition at that specific temperature. Okay, the line one end is called the pure nitromethane, which is 89.58 temperature boiling point. On the other end, which is x1 equal to 1, that means it is a complete pure acetonitrile. It's a 69.84, the boiling point. Okay, I hope now you understand the TXY graph. We are going to discuss detail about the PXY and TXY graphs in the near future. Okay, see you. Let us meet with the new lecture.